Hello, my name is Jim Olson, and this is a number theory video where we're going to show how to prove the divisibility tests. You may have learned the divisibility tests in school and wondered why they work. We're going to show you why they work. This is our video, this is our handout which we shared in week 1, and here are the divisibility tests. I don't think I'm going to be proving the divisibility test for 7, just to keep this video reasonable in length, but that that divisibility rule might be interesting as well. First of all, let's talk about a little bit of notation. So just as an example here, let's say we have 735. In expanded form, this is going to be 5 times 1 if you want, 5 times 10 to the 0 if you want, but I think I'll just leave it as 5, plus 3 times 10 to the first, plus 7 times 10 to the second. This is certainly an important idea in elementary school, but it is also what we worked with when we looked at base numbers. So what we're going to do here for these proofs is we're going to have the number written this way, an, then we might put an minus 1. I don't think I'll put that here. All the way down to, for example, A3, A2, A1, and A0. Now, I'm putting this in quotes. These are the digits of the number. These digits are not multiplied together. And if we put this in expanded notation, we have A0. That would be times 10 to the 0, but I don't think I'll write that. Plus A1 times 10 to the first, plus A2 times 10 to the second, plus A3 times 10 to the third, which is optional. You can put that in there. I think I've established my pattern, plus and so on, up through an times 10 to the nth power. This is going to be our notation. Now, this could be written in summation notation. I equals 0 to n of a sub I times 10 to the I. I think I'm going to not use that notation today, but it would certainly be fine. Okay, so let's do the proof. All of these proofs are going to have a similar flow. The first thing we're going to do is set up x. X is going to be, quote, an minus 1, an minus 2, a2, a1, a0. These are the digits that make up the number. So in expanded form, x is equal to a naught plus a1, 10 to the first, plus a2, 10 to the second, plus and so on, up through an, 10 to the n. N is going to be some integer, positive integer. Actually, I guess n could technically be 0 if we wanted to. Now we take our particular fact. A0 equals 0 or 5. That was our given information. That was in the if clause of our theorem. 5 divides 0, and 5 divides 5. This implies that 5 divides A0. So the last digit is divisible by 5. This is our particular piece of information. Now, I would like to look at a general fact. 5 divides 10. This implies that 5 has to divide the whole rest of the number. 5 must divide a1 times 10 to the first plus a2 times 10 to the second plus and so on up through an times 10 to the n. Notice that 5 is not dividing the whole number yet. It is dividing all of the number except the first term. But now I'm going to combine two statements, and we're going to be using our linear combination theorem again, which we use over and over in this course. I'm going to be combining that statement and this statement, and I'm going to be doing a very simple linear combination of these. 5 divides a0 plus this. A very simple linear combination. But this linear combination is x. 5 divides x. And this is my conclusion of the theorem. Now let's take a look at the basic flow of this proof. Here's the general flow. We set up x, the form of x. We have the particular divisibility test fact that is given. Then we have a general fact. We combine the facts and we get our conclusion. Let's look at another example so we see how this flow works. Okay, let's say we have an integer and 4 divides the number formed by the last two digits. Therefore, 4 must divide the entire number. Let's prove this divisibility test. We first of all set up x. This is an through a2, a1, a0. These are the digits of x. This means that x is equal to a0 plus a1 times 10 to the first plus a2 times 10 to the second plus a3 times 10 to the third, and so on up through an times 10 to the n. This will be our setup pretty much every time. Now we look at our particular fact. Our particular fact is that 4 divides the last two digits, a1, a0. That is, 4 divides a0 plus a1 10 to the first. That's our particular fact. Now we want our general fact. The general fact is going to apply to the rest of the number. But the rest of the number starts with 10 to the second, which is 100. 4 divides 100. And we might say why. The reason this is true is because 4 times 25 equals 100. This implies that 4 has to divide the whole rest of the number. A linear combination of 100 and all flavors of 100. So we have a to the second times 10 to the second, that is a to the second times 100, plus a to the third times 10 to the third, plus and so on up through our last term, which also has 100 built into it. Now we're going to do a linear combination of our facts. 4 divides a0 plus A1 times 10 to the first plus A2 times 10 to the second plus A3 times 10 to the third, and so on through AN times 10 to the n. Well, lo and behold, this is my whole number. So I can make my conclusion. 4 divides x. As always, you want to think about what's going on symbolically, but you want to think about the ideas and think about this conceptually. Now let me make a few comments about the converse of our statement. The converse of our statement would be that if 4 divides x, then 4 divides the number formed by the last 2 digits. That is also true. So these steps are pretty much reversible. Now we would be starting down here. Our given information would be here. We would set up x. The form of x would stay the same. And I would come up to this statement. The general fact is true. This general fact that 4 divides 100 and 4 divides from the A2 term on. Then what I would do is do a linear combination of this line and this line. And what I would do is take the double star line and add to it -1 times the single star line. And what that's going to do is subtract off the A2 times 10 to the second plus A3 times 10 to the third through the end. And then since I'm subtracting that off, I would come back to here and my final conclusion would be here. So the converse of all these divisibility tests could be proven. Now let's prove the divisibility test for 6. If x is an integer and 2 divides x and 3 divides x, then 6 divides x. This proof is going to be very straightforward and very short. 2 divides x and 3 divides x. Very typical in a proof that you start with your given information. We notice that 2 and 3 are relatively prime. Therefore, by a previous theorem, let's look back at what that previous theorem was. It's this one right here, that if you have 2 factors of a number that are relatively prime, then the product of the numbers divides the number. The product is going to be 2 times 3. 2 times 3 has to divide x, so 6 divides x. And we have proven this divisibility test. So this idea could be extended. For example, if you want a divisibility test for 12, you check for 4 and 3. Since 4 and 3 are relatively prime, you have a divisibility test for 12. Similarly, we could have a divisibility test for 14 or 15. This has been a number theory video on proving the divisibility tests. I hope it's been useful. Good luck in proving the rest of the divisibility tests yourself. Have a great day.